I do want to make a comment before we start. There are 7 problems. I really do believe that many of them are straightforward. And I also believe that you have the tools to answer all of the problems. You just have to make sure you've been practicing your tools. And there is a problem somewhere among the first 7, which will look a little different. And you might come to me afterwards and say, "You never prepared us for this one." And then I'll point to something. You'll say, "Oh, I guess you did." So everything that you'll see, there has been a foreshadowing somewhere on the practice problems, the quiz problems, so the review problems. So if you've been doing those and you feel confident, you should be in good shape. All right. So the biggest question, the biggest request by far I got was talking about power reduction. So we're going to start there. So to start, we have to review what trig identities should you know. So here's a list of all the trig identities that you are expected to know by heart. Let's just call this trig stuff. Trig stuff. There we go. That's easier to spell than trig identities. So you should know sine squared plus cosine squared equals 1. That relates directly to tangent squared plus 1 equals secant squared. And these are used very, very often. Basically, it says if I have a sine squared term, I can replace it with a cosine squared something, and vice versa. Similarly, if I have a tangent squared, I can replace it with a secant squared, or vice versa. Then we have the double angle one. So I'll start with the cosine. Cosine 2 theta equals cosine squared theta minus sine squared theta. Sine of 2 theta is 2 sine theta cosine theta. And then the final ones are the power reductions. So cosine squared is 1 plus cosine 2 theta over 2. And then sine squared is 1 minus cosine 2 theta over 2. And by the way, the power reductions actually come from combining the Pythagorean identity, sine squared plus cosine squared equals 1, with the double angle formula for cosine. So it's not very exotic. Now, the reason I left a little bit of a gap on the end is that the sine 2 theta, there's another way to think of it, namely that sine times cosine is equal to sine of 2 theta over 2. And in some sense, that can also be used for power reduction. So when I talk about power reduction, I'm really talking about, let's use these last 3. These are the power reduction identities. All right. So with that in mind, what's our goal? Well, when we're doing power reduction, here's our basic problem. We have integral of sine to an even, cosine to an even. And we're trying to do that. So if you see that, you need to do power reduction. If either one of them is odd, no power reduction will occur. All right. So that's when we use power reduction. When both the sine and the cosine are to an even power. What happens if one of them is odd? Well, the answer is if something is odd, what you're going to do is you pull off one to the end. You pull a term off, and that's going to become part of a du. So essentially, once you have one of them is odd, you're going to pull something off, rewrite everything in terms of the other, and substitution. And we'll see what that we mean as we go along. Okay, so that's what we need to know. Now, 2 examples, and we'll see how far we get. Sine squared of x, sine squared of 2x. Now this one, there's a little bit of misdirection here. You see, the insides don't match. Now, when the insides don't match, your first reaction should be, I want the insides to match. Because if they don't, game's over. And you stop. All right, so then the question is, how can we get the insides to match? So, one thing you might say, hey, I see a sine of 2x, I have double angle. But be open to other possibilities. What else could you do? Hint, other possibility. you can do, see, sine squared, basically, you can replace it with a double angle. See, and that has a double angle. So if you were to replace sine of 2x by 2 sine x cosine x, you'd essentially be going backwards. But if you replace the sine squared x by 1 minus this cosine 2x over 2, then you make a little bit of progress. So you can, of course, do both, just try something. Worst case scenario, try something, and if it doesn't work, well, you've got 75 minutes. That's enough time to try something else. Sine squared, 1 minus cosine 2x over 2. So that's the sine squared. And now it's sine squared of 2x dx. And now we're happy because the insides are consistent. They match. Good. Now it's a direct apples to similar type of apples comparison. That's the kind of thing we like. What happens here? Well, this will become 1/2 sine squared of 2x minus 1/2 cosine of 2x sine squared of 2x. So that's what we have. Now, what do we do? Well, the last one, and this is the great power about addition. It says, look, I can really think of this as 2 integrals. So I can make this 2 integrals and handle them each separately. The first integral, well, I only have sine and cosine to even powers. So my only thing I can do is when they're both to an even power, I've got to do power reduction. So we repeat power reduction here. So this integral, well, there's a half. There's going to be another half. That makes it a fourth. Then sine squared, that's the 1 minus cosine. And don't forget to double the angle. It's currently 2x. It would become 4x. And then there's this other integral. Now, here, what do? Well, see, we said if one of them is odd, that's the good news. Cosine is to an odd. Cosine to the first power, 1. 1 is odd. What that tells you is that's going to join with the dx and become part of our du. So what's our u? Well, if the derivative is the cosine, then that says you make the substitution of sine. So we set u equals sine 2x, and then we get that du is 2 cosine. Okay, I should have planned my space better. But we move the half across, and if you work this out, we have a half du, so there's another half, so that's 1/4. Then we got that du, and that's u squared. All right. And whoops, I forgot there's a dx here. There we go. And what do we end up with here? We end up with 1/4 x. That's the first term. Integral of cosine is sine. We're going to have to divide by 4. So that's a 16th sine of 4x. And here we're going to get 1/12 u cubed plus c. And to finish off, we say u is sine of 2x. So 1/4 x minus 1/16 sine of 4x minus 1/12 sine cubed of 2x. And there you go. I forgot to mention something about the trig identities. There are 6 identities which we expect you to know, the ones we just listed. There might be other trig identities which will be helpful, and if there is another trig identity which might be helpful, we will give it to you. So don't start trying to second guess. Is there a secret identity which we're expected to know? No. Those are it. That's it. Know that. But be prepared. We might give you something which is slightly different. Okay, so that's an example. And that took a little bit longer than I wanted, but all right. Sine to the 4th x, cosine to the 6x. How to approach this one? Well, I prefer the following. Do you see how sine times cosine, there's no plus or minus? That says, look, use that as much as you can, as much as you absolutely can. So here, well, sine to the 4th, cosine to the 6th says, I could really think this as sine cosine to the 4th. So I'm pulling off 4 sines, 4 cosines, and cosine squared x. So I'm preparing myself, and now I'll use it as much as I can. So that becomes sine of 2x divided by 2 to the 4th cosine squared 1 plus cosine 2x over 2. So then what do we have? Well, there's a 2 to the 4th, there's another 2, so that's a 1 over 32. Then you have sine to the 4th of 2x times 1 plus cosine of 2x. From here, well, we won't finish the problem, but we'll talk about where you go. You'd multiply the sine 4th to 2x through, and then you have a sine to the 4th 2x times cosine of 2x. All right, so that's what you'd have. Oh, there we go, something like that. Now, what happens from here? Well, that really looks weird. That's cosine to the 1. Just think of this as a 1. All right, what happens here is that this second term is ready for substitution, and life is good.
Where did the 1 over 32 come from?
2 to the 4th is 16, and then there's another 2. So that's 32. So that's where that came from. So the second term, again, once one of them is odd, you're set up. Substitution, life is good, and you stop. This one, sine to the 4th 2x, what happens from there? You got to keep going. It's more power reduction. You just keep chipping away. So that's what happens. All right, so that's and dot, but that's the general idea. Because we have other stuff we want to talk about. Okay. Next problem. This is from an old exam, not so long ago. Integrate from 0 to 1, x squared square root of 4 minus x squared dx. Okay, so what do we do? Well, first off, we have to identify what type of problem are we in? What type of problem are we in? Trig sub, right? Because you see a square root. Square root. A square root with a plus or a minus. When you see that, you should think trig sub. All right. Well, what kind of substitution to make? Well, this is the sine variety. So I'll come back and talk more about what type of substitution to make in a few minutes. So what do we get? We get that dx equals 2 cosine theta d theta. So we move along. X squared, so that's 2 sine theta squared, the square root of 4 minus x squared. Well, this has been set up to be nice. So this is square root of 4 minus 4 sine squared, which becomes, when you simplify, 2 cosine. So then the square root of 4 minus x squared, that's a 2 cosine theta. The dx is another 2 cosine theta. So, is there anything else? And the answer is, well, yes, there is. Well, what's the other thing? We've got the bounds. We've got to handle these bounds, 0 and 1. These are our x bounds. So how do we update the bounds? Well, we use our relationship. So at x equals 0, we get 0 equals 2 sine theta. So that says that sine of theta needs to equal 0. And they gave us a chart. So we start saying, well, when does sine of theta equal 0? Aha, there it is, at 0. So that tells us theta equals 0. So that's our lower bound. Then, do the same thing for the upper bound. At x equals 1, 1 equals 2 sine theta. Tells us that sine theta equals a half. So we start scanning. Where does sine of theta equal a half? Aha, there it is. So that tells us that theta equals pi over 6. And you might be wondering, would they actually give us the chart? We did. They gave the chart on the exam. If the chart, but I'll tell you what, pi fourths, 0, pi halves, you should know those. You should know those. When we start doing things like pi 6 and pi thirds, we're like, let's give them a chart. Let's give them a chart. Okay, so now we have another integral. Well, let's work it out. Let's count our 2's. There's 2 squared, that's 4. another 2 is 8, another 2, 16. So we're up to 16. Integral 0 to pi over 6. Then we have what? Sine squared and cosine squared. Well, what do we do? Well, the answer is power reduction, right? Sines to an even power, cosines to even power. So, well, one thing we can do is we can take the 16 and we can pull 4 off of that. So we can think it says 4, and it goes 0 to pi over 6, 2 sine theta cosine theta squared d theta. So that's 4, and it goes 0 to pi over 6, sine squared 2 theta. Well, and from here, more power reduction. So 4 integral 0 to pi over 6, 1 minus cosine of double that, 4 theta all over 2. So the 4 and the 2, okay, so that's 2. And then we integrate. Integral of 1 theta, integral of cosine 4 theta, sine of 4 theta times a fourth. We're going from 0 to pi over 6. So, what do we get? We get 2 times pi over 6 minus 1/4 sine of 4 times pi 6. That's the same as 2 pi thirds. And when you plug in 0, you get 0 and sine of 0. Now, sine of 2 pi thirds is not on the table, but we know stuff. We know stuff. So, for instance, think of the unit circle. So, pi thirds is here. This is pi thirds. Now, 2 pi thirds is like you go all the way to pi, and then you change your mind and go back by pi thirds. So the point is, it has this nice symmetry. And in particular, the y values are at the same height. So sine of 2 pi thirds is the same as sine of pi thirds. Well, sine of pi thirds is given to us. So this is 2 times pi over 6 minus 1/4 times the square root of 3 over 2. You can multiply it out if you wanted to. All right, so that's that problem. Now, there's a question. Somebody asked, how do we know what to substitute? So let me take a couple of minutes and do a quick review. So, when we have the form a squared minus u squared, which is the form we had here, our substitution is a sine theta. If it's a squared plus u squared, our substitution is tangent. So if everything's positive, it's coming up tangent. U squared minus a squared, then our substitution is secant. But that's actually not the whole story. It turns out that we can do the following. We could substitute, instead of sine, we could substitute cosine. Instead of tangent, we could substitute cotangent. And instead of secant, we could substitute cosecant. They're all equally valid. Now the question is, why do we train people to primarily use sine, tangent, and secant? The answer is because if you use those, you're less likely to have to deal with negative signs, because those derivatives don't involve negatives. But the others work just as well. Why don't we use the others as often? Well, again, because of the negative signs. That's the primary reason. Now, the question was asked in one of the emails I got, when do we use these? Because we have used them before. For example, one of our quiz problems used a substitution of cosine instead of sine. And the answer is we don't have to use them. So answer number 1, we don't have to. And you can avoid it if you can remember the following facts, namely that cotangent squared plus 1 equals cosecant squared. And if you remember that the integral of cotangent is minus log cosecant. And if you can remember that the integral of cosecant, oops, I forgot my d theta, that's embarrassing, is minus log cosecant plus cotangent. If you can remember those, then usually you're okay. A lot of people don't remember those. But if you can, you're fine. But here's the real answer about when we do it. See, if we swap, what essentially has is we flip the co. That's what it is. So if you made a substitution and you get to a certain point and you say, dot, 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 and eventually like, oh, I have to integrate cosecant. I don't like cosecant. I wish I could get rid of the co. The answer is, okay, come back up here and make the other choice. So if you make the other choice, what happens is, as you work through, everything stays the same more or less except for sign changes, and you either put a co in front of a trig function or you take a co out. So if it was cosine, it's going to become sine. If it was secant, it's going to become cosecant, all the way down. So that's the answer. If you make a substitution with sine, you end up with something unpleasant like an integral of cosecant or an integral of cotangent, and say, oh, let me just quickly change to cosine. Then everything becomes the kind of functions that you like to integrate. So that's what's happening. 95% of the time, stick with our tried and true ways. Don't try to change it. Only change it if you see something unpleasant coming in. All right. Any questions about trig substitution? Sometimes people are like, trig substitution is scary, but I think after we've been around for a while, it's like, okay, all right, not so bad. All right, good. It's not so bad, not so bad. Glad to hear it. Okay. Not quite exactly the problem that was asked, but close to one of them. Okay, so suppose you were asked to find the integral from 0 to 1 of e to the 2t plus 4, e to the 2t plus 4, e to the t plus 1. And that's all multiplied downstairs. One of the questions was, how do we start? That's a fantastic question to ask, because oftentimes if you can't even get started, it doesn't matter. Because if you just go off on a journey, we don't grade based on how much stuff is written. We have people who can write up 2 pages of computations, and we give out zeros and ones too. And then we have other people who write 3 lines, and we give 5 points. What we care about is, are you making progress? It's not how much you write down, it's how much progress you make. And so knowing how to start is really important. Okay, so part of it is knowing which type of problems you're in. In this type of problem, it's not clear where we're going. The other thing is sort of saying, okay, one of the things that you'll need to think about is, if the problem given to me is not clearly in one of my forms, let me think about ways to rewrite it. Are there trig identities I could use to simplify? Is there some simple algebra involved? And the other thing you should always be thinking about, hey, is there a nice clean substitution to make? So substitution, I know that's a Calc 1 thing, and we're like, yeah, we're Calc 2 people now. But you know what? The old ways are still the good ways. Substitution is your friend. All right. Now with that in mind, you probably know where we're going. What can we do on this problem? If we could do some substitution here. So for instance, this e to the 2t, that's really the same as e to the t squared. So everything really looks like something that has the form of e to the t. So a substitution that we could make, we could say, let's let u equal e to the t. And then du equals e to the t dt. Hey, that's what we have up here. That becomes our du. So we integrate, we update our bounds. E to the 0 is 1. E to the 1 is e. Upstairs, well, we just ended up with du. We'll put that on the end. E to the 2t plus 4 becomes u squared plus 4. And then e to the 2t plus 4, e to the t plus 4 becomes u squared plus 4u plus 4. All right. So one of the first things to do is, if you're not sure what type it is, think about a substitution to make. Now, the original integral is not so clear what we should be doing, but I claim that if we had been given this integral from the start, ignoring that we know what this is now, if we had just seen that, what type of problem are we in? This is partial fractions, because it's polynomial over polynomial. And now we're ready to go. Now, I don't know how far I'm going to get on this problem, but let's make a little bit of progress. Another question was, how do I know? How do I figure out what things look like? So let's sort of, at the very least, push this a little bit further. What's the next step in partial fractions? Yeah. Well, one could argue it's long division, but we know you should always double check. And then it's factoring. Is this factored? It's kind of factored. Is it factored all the way? No, not yet. What can you do? Aha, yeah, the second term is u plus 2 quantity squared. Okay, so again, we get the integral 1 to e of 1 over u squared plus 4 times u plus 2 quantity squared du. Now, here comes the question, and this is the point where a lot of people get confused. Let's try to clear up our confusion. Got to figure out the right form. So in particular, we now put the calculus to the side. Algebra commences. 1 over u squared plus 4 times u plus 2 squared. And here's what I want to draw attention to. How do you handle the squares? See, they're slightly different, and I want to make sure we know how to handle both of them. So, when it's a u squared plus 4, sort of think of this as your building block, what's inside your parenthesis. If that couldn't be factored any further, it really is like I have to have the u squared in there. All right? We call that an irreducible quadratic. It just means I can't factor it further. So this, it has the form of au plus b in the numerator. The u plus 2, that's been factored as far as it can go. That has the form of just a single term in the numerator. So you look at what's underneath here. Is it the u squared plus 4 or the u plus 2? So what's our decomposition? Well, we're going to have a single u squared plus 4. See, because it's to the first power, so it's just u squared plus 4. For the u plus 2, it's to the second power. That means we're going to have two terms, a u plus 2 and a u plus 2 squared. So we basically start at 1 and work up to the power. Because the u squared plus 4 is only to the first, we just need to go one time. U plus 2 is to the second, so we need to have 1, 2. And now, what goes upstairs is based off of sort of like the inside part. Here it's u squared plus 4, so it's au plus b. U plus 2, that's a constant. And u plus 2 squared, it's a constant because you're looking at the u plus 2. You're not looking at that square on the end, you're just looking at the u plus 2, d. Now, one check is the following. The number of letters that you have to determine, all the things you have to determine, should be equal to the degree of the polynomial downstairs. What's the degree of our polynomial downstairs? 4. And notice, A, B, C, D has 4 letters. That's a good sign. That means we're heading in the right direction. Okay, so what happens from here? Well, we can say that 1 equals au plus b times u plus 2 squared. So I'm multiplying by the denominators to clear out my denominators, plus c. U squared plus 4 times u plus 2 plus d times u squared plus 4. Now, I will tell you ahead of time, I have not tweaked A, B, C, and D to be nice. I suspect they're actually going to be quite atrocious here. But, all right. Suppose we wanted to go a little bit further. Now, what's our favorite technique? Choosing nice numbers. Will that always work? No. It won't always work. So you've got to be open to other options. What's another option? Because I think we're really good on the choosing nice numbers option. What's another way to do it? All right, it's good that we're reminding ourselves the other way to do it. Yeah, multiply everything out. Expand. Expand your polynomials. And then just be like, why couldn't they give us nicer numbers? That's what you'll think of as you do this part. So you just work on multiplying. I'll multiply the u plus 2 squared out here. I can start just, so what's the rule? It's like you just FOIL, right? And FOIL just means every pair gets a chance. So u squared times u, that's u cubed. Then there's a 2u squared, a 4u, and an 8. And, okay, that's u squared plus 4 is fine. So let's see, what do we get? We get au times u squared, that's au cubed. Au times 4u, that's 4au squared. Au times 4, that's 4a times u. Bu squared, 4bu, and 4b. Well, this probably was not the right way to do this problem, but all right, it works, right? Demonstration, it's proof of concept, you know. It's okay if we throw something out the window and it breaks. It's the idea that it might work. That's what'll sell the car. All right. So multiply the c through, and then you have the d times u squared and the 4d. All right. Now, so you were very patient, and you multiplied it all out. And let's just assume that it's true. I don't know, maybe. What's the next thing you do? Yeah, you come gather around. Come gather around. I have a story to tell. Now, how do we gather? We gather based off of the degree of u. So, how many u cubes are there? Well, I see a u cube there. So there's a, and I see u cubed there. That's c, and that's it. So that's a plus c u cubed. Okay, now what? Well, work down to u squared. There's 4a, there's b, there's 2c, and there's d. And that's your u squared. And then you work up to your u. So let's see, there's 4a, there's 4b, there's 4c. I think that's it, right? Yes. U. And your constants. Well, there's plus 4b plus 4d. That's 4b and 4d. Oh, and 8c. I almost missed that one. Okay, so there you go. Now, what happens from here? Well, from here, you take advantage of things. This polynomial, this is a polynomial in u, has to equal that polynomial, which is really 1 plus 0u plus 0u squared plus 0u cubed. And you're probably thinking, wow, why did we stop at 0u cubed? Couldn't we have written 0u to the fourth? We could have. We just need to get there. And now what you say is, hey, coefficients have to match. So here's an a plus c in front of u cubed. That has to match what's in front of u cubed. So we say, aha, look at that. A plus c is 0. The 4a plus b plus 2c plus d has to match what's in front of u squared. So 4a plus b plus 2c plus d equals 0. The 4a plus 4b plus 4c, that's got to match with 0. And finally, the 1 has to match the 4b plus 4d plus 8c. Now, this is a case when things are messy and it might take a while to solve. Or you just start thinking, well, what can you reason? We'll give you something which isn't so messy, if we give you anything at all. You're right, constant should equal 1. Somebody pointed out. I messed that up because there's a 1 there. All right, I'll point out, well, we have a few minutes. We can have fun, right? Nothing like, waking up in the morning, solving a nice system of equations. A plus C equals 0. What does that tell us about 4A plus 4C? 0. What does that tell us about 4 times B? Has to equal 0. So what's our conclusion about B? B equals 0. Cool. So that says we can throw that out, and that says we can throw that out. Okay. Let's see. What else can we say? Well, we have, well, let's use the fact, okay. Let's use the fact that C equals minus A. 4A plus 2C. Well, if I replace C by minus A, this is really 4A minus 2A. So this becomes 2A plus D equals 0, which tells us that D equals minus 2A. So now we'll come down here. We have 4 times D. Well, D is minus 2A, so that's minus 8A. Then we have 8 times C, and C is minus A, so that's minus 8A equals 1. So what should be true about A? Negative 1/16. So there's our A. We found B. What's true about C? Minus A, so 1/16. Okay, there's our C. And D? D is 1/8. Okay. Now you have your coefficients and you can go. So oftentimes it might look intimidating, but if you just work with the system of equations you get, it'll go pretty quick. Now there was a quick question that somebody had, and I'm going to not do the rest of the problem. They said, well, how do you go from something that looks like log of, let's say it's 2 plus 5e minus log of 4 plus 3e. Maybe we get an answer like that on the end. What can you do? And the answer is, one thing you can do is called circle it, because it's correct. A lot of people are like, how do I know when I can stop? You can stop when you've answered the question. That's when you can stop. If it says find this, once you've gotten a number, you can stop. The only time you can stop is if it says simplify as much as possible. But you can, of course, do things. So for instance, when you have subtraction of log, what can you do? Yeah. You could write log of 2 plus 5e over 4 plus 3e. These are equivalent. And then you could circle this. And the question is, would you get the same credit? And the answer is yes. We're not trying to test. You get exactly what we get. We are not my math lab. We're a little bit more forgiving. We recognize that sometimes there's slightly different ways to write the equivalent form. You need to get a correct answer. That's what you need to shoot for. All right. Well, I'll do a quick little side note. Someone wanted to look at this problem. So this is from an exam. Suppose we want to use the trapezoid rule to estimate the integral from -1 to 1 of 3 cosine squared of 2x minus 5. And it says, how many strips do you have to get so that your error is not so big? We want a kind of a smallish error. Now notice something. This part right here, this is on the test. It's not like we expect you to memorize the error formula. We just expect you to know how to use it. So it's like, wow, they've given us this error formula. Life is good. So we have this formula. All we need to do is figure out how to use it. So you have to understand the parts. Well, there are some things which are easy to spot. The B and the A are easy to spot because those are our bounds where we go between. So those are not so bad. The N, well, that is what we're looking for. See, it says find N. So this is what we're going to solve for, that N down there, which means that the only thing we don't know is the M. So we've got to really focus our energy on our M. And we want to say, well, this error is bounded by that. We'll come back to how to do that in just a moment. Okay, so what is M? Well, it would be nice if they told us, and so they did. They told us what M was. So M is a bound for your second derivative. How big can it be? A way to think about what M is to say, how far away are you from being a nice straight line? The bigger M is, the more not nice straight line you are. And of course, if you're a nice straight line, you should have no error. So, all right, so that's sort of the philosophy of what M is trying to capture. So where do we go? Well, this says, look at the second derivative. And the clue is that it says second derivative. So that's where we're going to go. So you have your function. Where's your function? Your function is what you're trying to integrate. So this is our f of x. So f of x equals 3 cosine squared of 2x minus 5. Now there comes a question. How do we differentiate it? And the idea is like, oh, differentiation is super easy, life is good, I don't have to do anything fancy. But we go back to sort of a philosophy, which is, can we simplify our expression before we do something to it? That's sort of a big goal of calculus, is just to say, I don't have that many tools. They're pretty simple. So what I need to do is take the current problem I have and make it simple enough so that one of my tools work. So is there something we can do to this expression to simplify it before we take a derivative? Do we have any good powers of trigonometry that might help us to reduce what's going on here? Yeah, there's power reduction. We can use power reduction. And you might say, but wait a second, power reduction is an integration thing. No, power reduction is a trig thing. Power reduction belongs to trigonometry. And we can use it wherever we want. So we can absolutely use it for integration, and we can use it for differentiation. So according to power reduction, there's 3. So cosine squared of something would be 1 plus cosine of double what's on the inside. So I'm going to double the 2x minus 5 to make it 4x minus 10, divide everything by 2. So we get 3 halves times 1 plus cosine 4x minus 10. So that's our f of x. Now we just go to work, f prime of x. Well, look, the 1, when we take the derivative, that goes away. So you have 3 halves, the derivative of cosine, negative sine, 4x minus 10, and then times 4, right? Because the derivative of 4x minus 10 by the chain rule. So clean that up a little bit. 3 halves times 4 would be minus 6, sine of 4x minus 10. But we don't want to stop at f prime. We want to go to f double prime. So minus 6, the derivative of sine is cosine, 4x minus 10, multiplied by another 4 by the chain rule. So we end up with negative 24 cosine of 4x minus 10. Now, our goal is to understand m. We ask ourselves the question, how big can this be? Well, the important thing about sines and cosines is that these are always between negative 1 and positive 1. That's one of the wonderful properties about sines and cosines that we use over and over again. So I have something which is going between negative 1 and 1. I'm multiplying it by negative 24. How big can I get? I can get up to size 24, whatever that is multiplying by. So the answer is, how big can it get? It's at most 24 in size. So I'm including plus or minus in that answer. So what does that tell us? Well, that tells us that 24 is what we were calling m. So now we know m. So we have 24. 1 minus minus 1 is also known as 2 cubed, divided by 12, n squared. That's this piece, this m times b minus a cubed over 12n squared. We want to have that, we know that's an upper bound for error. We want our error to be at most 1 over 10,000. So we say, look, make 1 over 10,000 bigger than this expression. Because this expression, our error is bigger than, our error is below our expression here. So if we can make this expression less than the number we want, then our error is definitely less than what we want. Some nice things happen. 24 goes into 12. It's almost like we anticipated that. So what do we have? We have 16 over n squared is less than or equal to 1 over 10,000. Flip both sides. If you flip both sides, what happens to your inequality? It flips as well. except I probably should have flipped both sides. That would have been more convincing. Okay, so n squared is bigger than or equal to 16 times 10,000. So now take the square root. Getting ahead of myself. Square root 16 times 10,000. Square root of 16, 4. Square root of 10,000, 100. So we get 400. So it means we have to do a lot of work. We're going to be using a lot of coconuts if we're stuck on a desert island doing that problem. But that's okay. We have unlimited supply of coconuts. All right, let's talk about an integration by parts problem. How do you recognize an integration by parts problem? Basically, you look for things like sines or cosines times polynomials. You look for e to the x times sines or cosines. That's one of those interesting ones. E to the x times polynomial. If you have arctangent or log, that's usually a big clue. Now, those aren't all of them, but those are the big ones. And so here we have integral from 0 to 1, square root of x times log of x quantity squared. So what does this become? Well, we have to say there's two parts, and here it's easy to see that there are two things multiplying. The part that you just don't want to integrate at all, that's the part we differentiate. So that we make the log x squared ru, the square root of x or dv. Du would be 2 natural log of x over x dx, because you use the chain rule to take that derivative. The integral of square root of x, well, that's x to the 1/2. So the integral of that would be x to the 3/2, and then you multiply it by the reciprocal 2/3. So we get uv, 2/3 x to the 3/2 natural log of x squared. Evaluate from 0 to 1. We'll talk about what that is in a second. And minus the integral of v du. So multiply these things together. And so you get 2/3 times 2 is 4/3. X to 3/2 times 1 over x is square root of x again. All right, that's x to 1/2, and then natural log of x. Now, one thing that should happen is if you do integration by parts, it should be simpler, or at least the same. If you do integration by parts and things are more complicated, you're doing it wrong. Go back and try the other way. Now, one of the questions that came up, other than the fact I forgot my bounds, okay, but one of the questions that came up is, how do we be careful doing integration by parts multiple times? Because we're not done. We have to do it again. And here's the truth. A lot of people are going to lose signs because of this minus. See, that minus sign, that's going to affect that whole term. So here's how you should be thinking about it. You should think about it as, oh, it's minus this expression. And so when you go through and you do integration by parts again, so this would be our u, so du is 1 over x dx. This will be our dv, and then we get that v, well, that's x to the 3/2 times 8/9. Then what we get is we get 2/3 x to the 3/2 natural log of x squared, evaluate from 0 to 1, minus parenthesis, then uv 8/9 x to the 3/2 natural log of x minus the integral of v du, which would be integral of 8/9 x to the 1/2 dx. See, so that this minus comes through. So don't forget it. Don't forget it. Now, from here, it's not so bad. You might have one concern, which is what happens to natural log of x as you go to 0? It's an asymptote. It blows up. So this part's going to infinity, and this part is going to 0. Well, what do you do? Well, you hope it goes to 0, and oftentimes these will, but how could you be sure? Use limit and use L'Hopital. All right, you don't always have to use L'Hopital for an improper integral, but if you don't know what to do, that can help. All right, well, I guess that's it for time. Good luck on the exam. See you on the other side when we start a new topic.